Hello viewers, in this lecture we are going to continue our discussion for the research paper titled New Discretization of Caputo Fabrizio Derivative. In the first part of lecture number 15, we started the discussion of this research paper and we derived a formula called L1 formula to approximate the Caputo Fabrizio derivative using linear Lagrange interpolation method. Let me also show you that formula in this research paper. So the formula, L1 formula in subsection 2.1 is given by equation 2.3. So in the first part of lecture number 15, we derived this formula 2.3 step by step, and we also designed its Matlab code. We verified our results with the results that are given in this research paper. Our today's goal is to derive the formula given in the subsection 2.2 called L1-2 formula. So in this subsection, the first part is backward approximation. So a quadratic Lagrange interpolation has been used. As you can see that using 3 points, this quadratic Lagrange interpolation can be written by equation 2.5 where j is from 2 to k. So the formula derived by the authors is given by equation 2.7. So once again, our purpose is to derive this formula 2.7 and then we will see how to design a Matlab code for this approximation. So this formula is called L1-2 formula to approximate the Caputo Fabrizio derivative, and authors have used the quadratic Lagrange interpolation technique and authors have called this as a backward approximation. So let's go to the derivation first and then we will switch to the Matlab code. So now here, this is the second part of lecture number 15. We are going to derive the L1-2 formula, derivation as well as Matlab code. So once again, as you can see that equation 1 represents the Caputo Fabrizio derivative. And now here in equation 1, I am going to replace x by xk. And if we do so, we will have equation 2. After that, equation 2, the interval of integration 0 to xk has been broken into several integrals, as you can now see in equation number 3. After that, I have written equation number 3 in a compact form, as now you can see in equation number 4 by using this summation notation. And now I am going to replace this first order derivative that appears in equation 4. This first order derivative, we can replace it by quadratic Lagrange interpolation using these 3 data points. So using these 3 coordinates, we can easily design the quadratic Lagrange interpolation polynomial, as you can see is written with this highlight, with this yellow color. So authors have restricted the above interpolation to this interval tj minus 1 to tj, as you can also see that we have the interval in equation number 4, integration interval, while j is from 2 to k. So remember, we have actually not considered here j is equal to 1. So later I will show you that why j has not been considered here, and if it is considered, then what kind of term we can have. Okay. So after this, I have also used these known relations from our knowledge of classical numerical analysis. So I am going to replace xj by jh in this yellow color expression. Similarly, xj minus 1 with this expression, and finally the last one. So if I replace, I will be getting this expression that you now see on the slide. After that, this expression has been differentiated because we need the first order derivative. So I have differentiated this yellow color expression and I have obtained this red color expression. After that, I have simplified it by collecting the x terms, and then you can see all the coefficients with fj minus 2, with fj minus 1 and with fj have been written. And once again, using the same relations, I can write down the relation, I can write down the equation in the form as written now in equation number 5. So it's a simple, it's a simplification for the previous equation given over here. So now we can easily substitute this equation number 5 into equation number 4. So you can see now from the previous slide, this equation, the last one is our equation number 4, in which now first order derivative has now been replaced by the left hand side of equation number 5, and now in the next step I am going to put this blue color expression into this integral. So if we do so, you will have equation number 6. So now you can see in equation number 6 we have exponential function. I have given this exponential function with the first term, as you can see, which is with s, and then with the other terms as well. So if I do so, I will have equation number 7. Little more simplification is required, and after that you will have equation number 8. Okay. So after equation number 8, you can see that I have integrated the term which was being appeared in the integral sign, and I have also substituted the upper and lower limit. So the red color expression has come after applying the integration and after applying the fundamental rule of calculus, while this blue color expression I have actually obtained after the integration. Now if I substitute the upper and lower limit in equation number 9, I will have equation number 10, as you can now see on the screen. So I would suggest that although you are looking at the presentation, you are watching the lecture, but when you will do it with your own hands, it will make your concept clearer. Okay, so just more simplification is required. I have taken this minus lambda outside, and then equation number 11 is obtained. After that, you can see that some terms will be cancelled because lambda, its value, remember from the first slide, it was alpha divided by 1 minus alpha. So 1 minus alpha has been cancelled and I am left with alpha here. So finally, I will have equation number 12. In this equation number 12, you can see it looks so messy and lengthy as well. So that is why the terms with the exponential function has been actually assigned a shortcut expression delta jk, and then similarly if there is j minus 1, then this expression is delta j minus 1k. So if I substitute these shortcut symbols into equation number 12, I will have equation number 13, which looks now pretty easy to understand. Okay, now the term. Do remember that we did not consider j is equal to 1 in the previous derivation. We started j from 2 as the authors did. So what happens when j is equal to 1? So here I would suggest you that you must watch the first part of lecture number 15, and after watching that you will understand easily that if I put j is equal to 1, I will be having this last equation that you now see at the end of the slide, and I'm also going to highlight it. So after putting j is equal to 1, you will have this kind of equation. So I can add this equation to equation number 13, which is actually from j is equal to 2, as you can see from here that this expression is when j is starting from 2. So when j is 1, you will have this last expression. Okay, fine. So add the first expression as well into equation number 13. So finally, you will have equation number 14. Here, do remember that in many research papers as well as the one we are considering in our current lecture, m of alpha is a normalization factor which is taken to be 1 in several research papers. So we have also taken here m of alpha as 1. So if we put this into equation number 14, finally we will have our required scheme called L1-2 method, backward approximation for the Caputo Fabrizio derivative. Now compare this final obtained scheme with the scheme that has been given in the research paper. You will find no difference. Let me show you the research paper as well. And the scheme in the research paper is 2.7, exactly the same scheme we have obtained after this derivation. So you can see that the derivation has taken about 10 slides, and here it was so directly given and there was no simplification, and believe me, it gave me a tough time to get the to reach at this equation number 2.7. It requires a lot of simplification. And after that, I was able to obtain this final scheme. I hope you understood the derivation. Now, after understanding the derivation, it's time to understand how a code can be designed for this final scheme called L1-2 method. So let's go to our M file to understand its Matlab code. So let's go to the M file. So as usual, you can see that on line number 11, I have written some necessary commands. Then some inputs start. You can see on line number 18, we have the step size. Line number 22, we have initial value. Line number 25, we have the final value. Line number 28, we have our interval starting from the first and the last with the gap h. And then line number 31, we have number of steps, k. And then fractional order 0.1 I have taken. You can take some other number as well. This normalization factor on line number 37. And then the lambda, which has been defined as minus alpha upon 1 minus alpha. After that, w is equal to 4 because this number is being used on line number 51 for the function that I have taken for the numerical simulation as cosine wx or cosine 4x. So now finally the algorithm starts. You can see that j starts from 2 to k on line number 57. After that, since the scheme was quite lengthy and when I was typing the entire scheme in one line, I was forgetting to put some brackets, so it was giving me tough time to understand how the code can be easily typed. So that is why what I have done, I have broken the code into some terms. Like you can see that this term has been assigned a name first, and then some other terms I have taken and assigned a name C on line number 63. Similarly, you can assign some names for some expressions in the code. In the scheme, let me show you the scheme. You can say it's quite lengthy scheme, so you can break it. For example, the first one with the red color, I have assigned a name first, okay, and then the part with the green color, you can take it as C. The part with the, for example, this white color, you can take it E, J, and so on and so forth. And after that, putting these letters into the main scheme given on line number 74 makes it easy to understand and to avoid any bracket, any mistake that is related to the brackets. So I suggest you to break the terms into several terms and then use those letters into your final scheme as I have done on line number 74. Okay, fine. I hope it gives you some understanding. If you type it by your hand, I hope it won't be difficult for you. So let's go to the exact solution now. So a symbol X has been introduced on line number 80, and on line number 86, the exact solution has been computed. As you can see, it's a definition of Caputo Fabrizio, the same definition I have written here, no any change. And then I have converted the answer obtained from this line number 86. I have converted into the double precision. And then on line number 96, you can see that I have actually computed the absolute error. And after that, I have displayed the results, and finally, you can see that the results are shown on line number 108. I will have number of steps. When I will run the code, I will have the results on our command window, and then I will see how many steps are taken, what was the step size, what is the exact answer, what is the approximate answer, and what is the absolute error. Fine. So let's go and run this code. I'm going to hit the run button, and then I'm going to see the result on the command window. You can see here we have our results, as now you can see on the command window. 20 steps are taken with the step size 0.1. Minus 1.0811 is the exact answer. You can see the approximate answer, and the error has a magnitude 10 to the power minus 5. Let's verify these results from the research paper. So cosine 4t in the research paper has been taken in this second example. So let me check where is the table where the simulations are given. So we have table number 3 here. So I will have to go to the table number 3. So let's go to table number 3. So here we go. Okay. So here we go. With the step size 0.1 and the fractional order 0.1. Look at this. What is the result? The results given in the bracket are actually the absolute errors, which are computed at the final mesh point, which was true. Okay, which was 2. And we have taken the same mesh point. So note down the absolute error here. And see that we have also obtained the same error, 6.3310 to the power minus 5 with the step size with the fractional order 0.1. Let's confirm the second one. So if I run the code again with the step size 0.05, then let's see what we are going to obtain. So we have 10 to the power minus 6. 7.214 to 10 to the power minus 6. Let's confirm it from the research paper and look at the amount of error. We have the same, 7.2110 to the power minus 6. Okay, in my last lecture I had told you that I will show you how these rate of convergence is going to be actually computed, how the rate of convergence is computed. So you can see it is about 3.13 and around 3 in every simulation. So the formula actually used by the authors is given at the start of this section. You can see the formula they are using is this one. Let me highlight that formula. So it is actually this formula, right? So the formula is actually this one. So log to the base 2. The error with the step size delta t, and then divided by error with the step size half of the previous step size. So let's use this idea and verify the rate of convergence. So now I'm going back to 0.1 and I'm going to run this script, and let's see, this was the error. I'm going to note down this error and I'm going to call it as E1. Okay, and then I run the script again with half of the step size. Okay, and now I take this error as well and I will call it as E2. Okay, so now according to the formula, log base 2 and then E1 divided by E2. Let's see what's the result. Okay, I didn't actually E1 and then I have E2. Now I can use the formula and then you can see we have 3.1335. Approximately 3, the rate of convergence is verified. And I have also told you another way of confirming the rate of convergence. You can decrease the step size by 1 order of magnitude, and if you observe the 3 orders of magnitudes decrease in the absolute error, it will give you the confirmation that your method is 3rd order accurate. So there are 2 ways to confirm the rate of convergence. Okay, I hope you understood the derivation as well as the code of this L1-2 method that the authors have actually obtained via quadratic Lagrange interpolation and called it backward approximation. So I hope you understood and enjoyed the lecture. If you have any queries, any questions, these are welcomed in the comment box. Thank you so much for watching the lecture.